Hello, my name is Zhongkai Zhang, application engineer at Habana working on TPC Kernels. This video is entitled Gaudi Intro to TPC Kernels, which target to some developer with experience on AI model and want to create their own custom kernels for more advanced performance. Today I'm going to talk about three topics. First, what are TPC and the TPC kernel? Then we will introduce Habana tools and show you how to install and use it. Last but not least, how to write TPC kernels using Habana template project we provide in GitHub. So let's get started. The TPC Core was designed to support deep learning training and inference workload. We have 8 TPC cores integrated to every Habana processor. They were designed for customization and they were fully programmable via AW4 DSP core for workloads that do not map to MME. Habana provided extensive 1400 plus kernel libraries to enable workload and operators to be implemented. For Gaudi, the TPC Core native support the data type including FP32, BF16, signed and unsigned, 8, 16, and 32 integers. The kernel library Habana provided is usually enough for excellent performance, but in some cases, depending on the application, the users may want to develop their own kernels, even their own custom apps. We create this Habana custom kernel template to make the kernel development much easier. So the following video, I'm going to show you how to do that. So first thing first, how to install the Habana tool. So we have a tool called the Habana tool, which is the kernel creation tool. This tool will compile the TPC kernel code and build the custom kernel library, then run on the simulation to verify the correctness of the kernel. What I will show you in this video is to download the latest package by visiting its GitHub page and install the tool to your system. So there are instructions on the GitHub page. So after you click the Habana Vault link, it will bring you to this web page. They show you the latest package. So you either click the top right corner download button or use the URL to file to get the latest package. So we have the regular release of the package, so make sure you check and always choose the latest one. Here I just used the Ubuntu 18 as example. The tool is also work on other supported OS. Since I already have the package downloaded, what I will do next is run this sudo dpackage command. dpackage-i. After done, you can check those files already in your system. Let me run this command. Here you can see there's a TPC compiler and the simulation library and some of the C header file, including the TPC intrinsic. Now we have the Habana tool installed. The last but not least, I'm going to show what the TPC kernel and the glue code looks like and how to write the custom TPC kernel using the template project we provided in the GitHub. So please visit this GitHub page to clone the repo. So make sure you create as public key and add it to your GitHub's profile and run git clone. So let's follow the steps to write your own custom kernels. So first, write the TPC kernel, which will run on our Habana device. Second, write the glue codes, which set up the kernel and load the kernel library. I will talk about the glue code in a second. Then write unit test, which is optional, but it's necessary to verify the correctness of the kernel. After that, use cmake and make to build the kernel library. Last, add the kernel path to gc kernel path to this environmental variable. Let's just read back to the demo and go through all those code. So you can see here we have the 3 folders. We have kernel, source, and test. So inside the kernel, we have the Gaudi. Gaudi folder contains all the kernels will run on the Gaudi device. So let's use the filter as the example here. So TPC kernel is written in the TPC C, which is the C-like language with the PBC intrinsic. So every kernel has the main function. It has input and output tensor and the scalars parameter follow. So in every kernel, we always start with getting the start and end coordinates of index space using these 2 built-in functions. Then we use the load intrinsic to load the tensor and the store intrinsic to store the output tensor. So different data type has different loads and the store intrinsic. To implement the kernel function, we use the TPC intrinsic to maximize the TPC performance. For the definition of each TPC intrinsic, you can check the developer website for more detail. So second, let's check what's the glue code. So inside this SRC folder, we have all the glue code. So glue code, a piece of code to set up the kernel parameter and load the kernel binary to graph compiler. So the glue code run on host, not on Gaudi device. So two major functions, so get kernel names and get the GC definition, or Habana kernel name doesn't really matter. So function get kernel names is to get the kernel GUID, which is used to identify each kernel uniquely. So function get GC definition is the main part of the glue code. To check the number of the input and output tensor, verify the dimension of the tensor, set up the index space, and load the kernel binary to memory. We also have the global entry point for all the glue code. So the last component is the unit test. So in each unit test, there are two parts. The first part is the reference code implementation, whose output are used to validate the kernel output data. Another one is the main part is the run test function. It contains the main text body, which initializes the input-output tensor data, call the kernel entry point, and run using the simulation and compare the output with reference. Now let's show you how to build the kernel library and along with the unit test. So we have created the CMake list file to simplify the build process. The first thing is let's go back to this folder. Let's create the build folder. Let's see the build folder. Do the CMake. Then do the make. So what make does is call TPC compiler and generate the TPC library and also create the unit test executable binary. So we don't have a lot of the kernel in this template project, so the build process should be quick. So in this, after finished, you can check the SRC folder. It has the customer TPC library generated. We also can run the TPC test executable. Yeah, you can see it runs through all the unit tests and everything passed. So for multiple kernel library, we need to set up the environmental variable GC kernel path with each kernel library separated by colon. So customer kernel library usually goes first. For more detail, you can always visit Habana developer website or read the doc. So finally, let's summarize what we learned today to create the customer kernel. So install the Habana tool, use the package you downloaded. Develop the kernel using template project. You will have this shared library created. Third, explore the library you just created to the GC kernel path, which will be used by graph compiler. The user can also create the TensorFlow custom app using custom kernel you just created. Please visit the following website for detail. Thank you for watching. For more detail, please visit developer.habana.ai. Thanks, bye.